Hi, everybody. It's a pleasure to be here virtually. My name is Dmitrii Ostrovskii. Currently, I'm an assistant professor of mathematics, non-tenure track at USC. I had a postdoc previously at the engineering school of USC Viterbi. And before that, a short postdoc at the IN Research Center in Paris, in France. I also got my PhD from France, and I do speak French. So let me first, briefly sketch my research agenda. So on a very high level, it has to do with two aspects: statistical inference, well, two streams, two directions of research. So the first one is statistical inference, in particular focused on finite sample guarantees, small sample guarantees, or high dimensional data, and adaptivity with respect to unknown structure and robustness. Now, the other meta direction is optimization theory, in particular in the context of large-scale optimization, first-order algorithms, but also second-order algorithms, and taking into account curvature. Now, these two directions, they inform each other, interact with each other. To give you like two hints at how such an interaction occurs. One is, you can, well, first of all, if you think about statistical inference, then oftentimes you also require, well, typically in practice, you require the inference procedures, inference routines to be tractable. And then they are oftentimes given as solutions of optimization problems that you can efficiently solve. Particular convex optimization, but not necessarily convex, other kinds of post-structure optimization problems. Now, then advanced knowledge of advanced optimization techniques usually facilitates your statistical analysis. Okay, in particular, you might start, for example, writing down the first order optimality conditions, and then your statistical analysis will grow from there. Or another example is that you might incorporate an exact knowledge of your estimator, because you might not be able to compute, and you typically are not able to solve optimization problems precisely. And then this optimization accuracy error gives you an estimate of how well you should, what is essentially your statistical accuracy. Now, in the other direction, you might think about general optimization problems, not necessarily related to any sort of data fitting or parameter fitting from the data, from random data, from distributions. But even in this case, you might consider randomized algorithms. So making an algorithm stochastic allows to accelerate it typically. But on the other hand, you lose in accuracy, right? So because you don't minimize what you were intending to minimize previously. Now, the question is, when you aim at establishing this kind of computational trade-off, how much you lose and how much you gain, typically you need to use advanced statistical techniques. Just very briefly about my research philosophy, I emphasize quality over quantity. My ideal is a fresh idea, well-rounded story, ideally is a closed problem or a new problem in each paper. This has to be taken into account when judging my productivity. Now, another thing is I strive to work in several areas, and my research tends to be rather multifaceted. I'm a flexible collaborator. I flourish in collaborations, and I enjoy them very much. And one thing I enjoy in particular is to guide technically strong junior collaborators using my vision and erudition and taste to problems. Finally, my main drive is to work on foundational questions, but choice of these questions and even particular progress of working in the project is oftentimes application informed or even constrained by practical considerations. So I might start working on something from, after a conversation with a practitioner, and then I also preserve this practical requirements for practical constraints when carrying out the framework. So now, two very brief examples of my achievements. So one is I was able to characterize the threshold, the essentially precise threshold where of learnability for for M estimators with smooth losses, in particular logistic regression random design. So it is known from the classical statistical asymptotic theory that the right kind of error in some sense for the large sample size, the right error, so the margin of how fast you approach well, what is your error with sample size n when you try to estimate d parameters from your data? How does it behave with d and n? Then it turns out that the right answer is d over n when n is very large. But the practical question is when, like what finite n suffices, okay? And what has been known for this problem, the state of the art was essentially quadratic threshold that n roughly scaling as d squared suffices, okay? And then I was able to establish essentially under the same assumptions, which are also minimal and reasonable assumptions for this class of problems, that the right threshold is nearly linear in the sample size. Sorry, the right threshold for the sample size is nearly linear in the parameter dimension, the number of parameters to estimate. Okay, so to give another example, one topic in optimization that I've been active recently in the past 2 years was Minimax problems beyond the convex concave, the classical convex concave scenario. So classical convex concave Minimax problems, they were introduced in the 1940s, basically by the seminal works of von Neumann and Nash in the context of game theory. So as a like blueprint for modeling zero-sum games. Now, the thing is that convexity concavity of your functional, so you can think about such problems as minimization in X, the X player of the maximum in Y, the Y player of f of xy, where f of xy is a certain utility function. Now, making this function convex in X and concave in Y allows for computational tractability, while at the same time allowing the theory to be rich and cover like many practical scenarios. But recent applications such as robustness, such as adversarial training, or for example wireless networks modeling, calls for going beyond this convex concave scenario. So in particular, in 2 recent works, I was first able to propose a state-of-the-art algorithm. So an algorithm with state-of-the-art computational guarantee for solving non-convex concave problems first, and the complexity is also conjectured to be minimax optimal, but it's still an open problem. And another contribution is to consider non-convex non-concave problems. But instead of requiring concavity, you make the nested maximization problem solvable in some other way, namely by simply restricting the set of adversarial strategies, so the set of Y on which you maximize over Y. Then it turns out that this is really a very benign problem statement. It turns out that you can characterize the precise threshold of the diameter of your maximization set with which such problems become solvable by performing Taylor approximations.